Oh, wait. Imagine this. A completely new phase of a matter. I mean, something that sounds like it's straight out of science fiction. And now imagine that new matter could, totally change the future of computing. Sounds pretty wild, right? Well, it seems it just happened. Welcome to the deep dive. Today, we're jumping right into Microsoft's, frankly, astonishing announcement about something called Majorana Zero Modes, and why they might just redefine quantum computing completely. This isn't just a small step. It feels bigger. So our mission today is pretty clear. We want to unpack what this new matter really is, why it's such a massive leap for quantum computing, and, what it actually means for all of us for the future. We're aiming to give you the key stuff without hopefully getting too bogged down in a really complex jargon. We're pulling from some detailed notes here titled Microsoft's Majorana Breakthrough, A New Quantum Era Begins. Trying to get the core ideas. Okay, let's get into it, because honestly, this discovery is genuinely mind-bending. So first off, when Microsoft talks about a new form of matter, they don't mean a new element for the periodic table. Right.
No, exactly. That's not it at all. It's what physicists call a topological phase of matter. Think of it more like a unique quantum state, where particles just start behaving in fundamentally new ways, almost like they're following a different rule book.
A different rule book, okay. And right at the heart of this are these Majorana Zero Modes, MZMs.
That's right. MZMs are these exotic things called quasi-particles. So not fundamental particles like electrons or photons. They kind of emerge from the way the whole system behaves.
Okay, emergent properties?
Yeah. And the really wild part about these Majoranas, they're their own antiparticles.
Whoa! Okay, their own antiparticles. That's
It is. It's a concept that's been, theorized about for decades, like 80 years or more.
Yep.
But it was always just theory. Now they've actually observed it in a system they built.
So it's gone from abstract math to something real.
Precisely. That's what's so fascinating here. Taking this decades-old theoretical prediction and actually making it happen in these engineered quantum systems. It's one thing to describe them mathematically, but it's a whole other challenge to build an environment where they reliably appear, and crucially, where you can control them. It really bridges that gap between abstract physics and hard experimental proof.
Okay, so they're exotic, they're their own antiparticles. But why are they so important for quantum computing specifically? We always hear about qubits being fragile.
Exactly. That fragility is the number one headache. Traditional qubits, the building blocks now, are incredibly sensitive. Heat, radiation, just tiny vibrations in the environment. They can all mess things up, knock them out of their quantum state.
Which makes the whole error correction thing a nightmare, I assume.
Oh, absolutely.
Yeah.
Quantum error correction is extremely complex. You need tons of extra qubits just to try and keep the main one stable, even for fractions of a second. It's a huge overhead.
Right, so how do Majoranas help with that?
Well, because they enable what are called topological qubits. And the key is that word topological.
Yeah.
Because of their fundamental nature, this topology, they're inherently error-resistant by design.
Error-resistant by design? How does that work?
It means the quantum information is stored sort of non-locally. It's encoded in the relationship between Majoranas, not just in one single particle. So a small local disturbance, like a bit of noise, can't easily corrupt the information. It's like it has this built-in protection.
Ah, okay. That makes sense. It's not all in one vulnerable spot.
Exactly. And because of this, they also have longer coherence times. They can hold their quantum state for much longer.
Longer coherence.
More stability.
And critically, they seem to be scalable. They offer a much more solid foundation if you want to build really large practical quantum computers.
Okay, I think I'm getting it. I used this analogy earlier. Maybe it works. If traditional quantum computing is like trying to build with dry sand,
it just collapses easily. Then topological quantum computing with Majoranas is like building with Lego bricks. They snap together, they hold their shape, even if the table shakes a bit.
That's a great analogy, yeah. The Lego bricks hold their structure because of how they connect, not just because of one fragile piece. That's the topological idea. Stability through structure.
It sounds almost too perfect. Are there downsides? Why isn't everyone doing this if it's like Lego?
Ah, well, there's the rub. Building those Lego bricks, creating and controlling Majoranas is incredibly difficult. The engineering is immense. You need extremely low temperatures, very precise materials, specific magnetic fields. It's much harder to get started.
Okay, so it's not easy.
Not at all. That's why you see giants like Google and IBM focusing on other types of qubits, like superconducting circuits or trapped ions. Those might be, let's say, easier to build and control in the short term, but then they face those huge error correction challenges down the line.
So Microsoft's playing the long game here, betting on stability even if it's harder now.
It certainly looks that way. They're prioritizing that built-in fault tolerance, aiming for the stable foundation first. It's a different strategy. Definitely high risk, high reward.
Fascinating trade-off. So the Lego analogy holds, but building the factory to make the Legos is the hard part.
Something like that, yeah.
Okay, so let's get into how they actually built this Majorana factory. How did Microsoft manage it?
Right, the experimental setup. Well, simplifying it a bit. First, they had to engineer a nanowire platform. This involved layering specific materials, really precisely supercooled semiconducting nanowires and superconductors. Think incredibly tiny, intricate structures.
Like a microscopic quantum sandwich.
Yeah, a very carefully made sandwich. Then they had to create the right conditions. They induced a topological superconducting phase by applying just the right magnetic fields and voltages. It's like tuning an instrument perfectly.
Okay, so build the stage, then set the lighting and sound just right.
Exactly. And then they looked for the signal. They observed signatures using a technique called tunneling spectroscopy. And what they saw was this specific thing called quantized conductance. This is described as the hallmark signal for Majoranas.
Quantized conductance. For us non-physicists, what does that actually mean? What does it look like?
Basically, it means the electrical current flowing through the device doesn't increase smoothly as you change the voltage. It jumps up in specific, discrete steps. And crucially, there's a peak, a jump, right at zero voltage, a zero bias peak that has a very specific height or conductance value.
So it's like a very specific fingerprint in the electrical current. If you see that pattern, and especially that specific jump at zero,
then you know you've likely got Majoranas. But they didn't just stop there. Seeing it once isn't enough in physics.
Right, you need proof.
Absolutely. They subjected it to this really rigorous 6-step experimental protocol. This involved checking for things called topological gaps, making sure that quantized zero bias peak was really robust, that it stayed there even when they changed parameters like the magnetic field slightly.
So really trying to break it or rule out other explanations.
Exactly. They were essentially passing a smoking gun test, proving these signals weren't just some fluke or artifact, but genuinely the signature of controllable Majorana zero modes.
Wow, that level of rigor sounds critical.
It is. For something this potentially groundbreaking, you need incredibly strong evidence. And this protocol provides that. It really raises the confidence level significantly.
Okay, so they've done it. They've passed the test. This feels like a really big deal then for fault-tolerant quantum computing.
It is. Because having qubits that are naturally immune to local noise fundamentally changes the game for stability and scale. You're not constantly fighting errors. You're starting with something inherently more robust.
And you mentioned Microsoft's strategy. This bet on topological qubits is unique among the big players. This result must really validate their approach.
Absolutely. While others like Google and IBM are making progress with their systems, often called NIQ systems, for noisy intermediate scale quantum.
Right, the noisy ones we talked about.
Yeah. Microsoft's achievement here opens the path to Microsoft's quantum supercomputer vision. It suggests they're aiming directly for scalable, fault-tolerant machines, not just bigger noisy machines, but fundamentally stable ones.
So skipping the intermediate noisy step, almost.
Or at least focusing the main effort on the fault-tolerant end goal from the start. It's a bold move.
Here's where it gets really interesting then. This isn't just a step. It potentially feels like a leap towards a different kind of quantum future.
It could be. It definitely raises that important question. Will this focused bet allow them to potentially leapfrog competitors in the long run when it comes to building machines that can actually solve currently unsolvable problems?
High risk, high reward, like you said. Okay, so what happens now? What are Microsoft's next moves after this?